Hello and welcome to Doc Plays Chemistry Lessons. Today we're going to be looking at polymers, and in particular we're going to be looking at condensation polymers. By the end of today's lesson then you should be able to do the following. You should be able to know how to make polyesters and polyamides, identify monomer units in these polymers, recall specific examples of terylene, nylon and Kevlar, discuss the disposing of polymers and condensation polymers, and identify polymerization in amino acids. There's two main types of polymers then that we look at. The first is the addition polymers, which we looked at in the AS course, and you can check out the video at the end of the session here, and condensation polymers. The key then about our addition polymers, you remember, they all had the carbon-carbon double bond, which opened up between the polymers, and that went on to form an addition polymer with a carbon-carbon single bond. Condensation polymers then we'll be moving on to look at in just a moment, come into two types, and they come into either polyamides or polyesters. The common thing in both of these reactions is that when we form the polymer, we also form a byproduct, or a small molecule, often of water, or sometimes we can also form hydrochloric acid if we make it with a acyl chloride. Generally though, we tend to see the formation of water. We're going to go and look at polyesters and polyamides now. Polyesters then are polymers which contain the functional group of an ester link. You can see the ester link here, the functional group, which has got the C double bond O in it, making a polymer and hence polyester. The polyester then can be formed, in this case, from two different monomer units. We can have the dicarboxylic acid, and then we've got an alkyl group between the two carboxylic acids, just shown by a square, and a diol, the alkyl group between the two alcohol groups here, shown by a grayed out circle. These will react together in a condensation reaction, and they will form and react, and as they react, they will release a molecule of water, and importantly, per repeat unit, so that is from here all the way up to this endpoint on the other side here, they will produce two molecules of water per repeat unit, because there's two ester bonds being formed. So our ester here is made from a dicarboxylic acid and a diol, and we're now going to go and look at a couple of specific examples. Our first polyester example then, or polymer condensation polymer, is terylene, which has got used in plastic bottles, as well as clothing, sheets, and as well for sails on boats. Terylene then is made from these two monomers. We'll deal with the easy one to start with. We've got here on the right hand side ethane 1, 2 diol. We have to specify the position because the alcohol could be on either end of the carbon, so it could be on both on the first carbon or on the first and the second. And then the other monomer, which is a little bit more difficult, is benzene here, and then it's 1,4-dicarbonyl carboxylic acid. So once again, we've got the diol and the dicarboxylic acid. We react these together then, and what happens is we get the condensation, the hydrogen from the alcohol and the OH from the carboxylic acid come off. These come off as water. And what we end up forming is the polyester, which, as we've said, has got the trademark name of Terylene. The ester bond here forming in the middle, and we've also got the second one here on either side. And overall, we have the repeating unit, which we put in the square brackets. Okay, so now we're going to go and have a look at the polyamides. The polyamides then are formed between the dicarboxylic acid again, as we saw with the polyesters, and instead of the diol, we've then got a diamine. This time in between we can have an alkyl group, and again we'll see that these can be either simple carbon chains or they can be slightly more complex benzene rings. These will polymerize again, and per link that is formed there'll be one water molecule. So we'll see as we tend to form one whole polymer, we'll get two water molecules per repeating chain. We form between these two molecules then the amide link, and we'll see in the future videos when we look at amino acids that if this is an amino acid, we actually then can call this a peptide link. Just be aware though, we only ever really call this a peptide link when we're talking about biological systems and amino acids. We're going to go on and look at two important examples of which we need to be aware. We're going to be looking at both nylon preparation and Kevlar preparation of types of polyamides. Polyamides then, we'll look at this example of nylon, which have long been used for things like clothing and making ropes, as well as carpets and other things like parachutes, to name just a few. Nylon was first called nylon because they thought when they were first making it that it would stretch from New York to London, and so that's where the acronym nylon first came from. Once again, we've got a dicarboxylic acid, and here we've got hexane dioic acid. And actually, of course, that should be hexane dioic acid. There should be an E in there. And here we've got 1,6-diamino hexane. Once again, we get a condensation reaction between the OH and the hydrogen, forming our amide link. And again, because we've got a water molecule on either end produced, we form two water molecules per repeating unit. In this example, because our carbon chains in each of our monomers both has 6 carbons, we call this nylon 6-6. However, if we have different length alkyl chains or carbon chains between the carbons and between the nitrogens, we can alter the name of the nylon, so we end up with things like nylon 4,6, nylon 6,4, nylon 1,6, and so on and so on. So the numbers here represent the number of carbons in the carbon chain between the nitrogens and the carbon chain essentially between the oxygens, the carbon double bond oxygens. Here though, we're making nylon. The final condensation polymer we're going to look at is a polyamide, and it's called Kevlar. Often used for things like bulletproof vests, boat construction, and also lightweight sports equipment, because it's very tough and can withstand a lot of shock and impact. So here are our monomers that the Kevlar is made from, and once again we've got our benzene, and we've got the positions of 1,4-dicarboxylic acid, and this time we're reacting it with a benzene ring, but this time it's the 1,4-diamino benzene. Again, as we've seen with the other reactions, we form condensation reaction with the OHs and the hydrogens, and per repeating unit, once again, we produce 2 water molecules. The product then is an amide. It has a amide link in, and it's a polymer, so it's a polyamide, and this one has got the trademark of Kevlar. Each of these 3 polymers, that's Kevlar, nylon, and the terylene, are required for the AQA syllabus. In the final part of this video then, we're just going to look at the intermolecular forcing condensation polymers and also how we can break them down. Polyamides, as well as polyesters, have the situation where there is a lone pair of electrons on the oxygen and the hydrogen, and also a lone pair of electrons on the nitrogen, and these can interact and form strong hydrogen bonds between the polymer strands. And what this does is it means that the intermolecular forces are very strong, and the polyamides as well as the polyesters tend to be stronger, more rigid than the addition polymers, and that's simply to do with the fact that they're able to form stronger intermolecular forces such as these hydrogen bonds. The final thing we're going to look at then is how we can actually biodegrade condensation polymers. Before we move on and look at the breaking down of condensation polymers, we should just have a brief look here at what happens if we have a single monomer unit condensation polymer. So we don't have to have a dicarboxylic acid and a diamine to make a condensation polymer. There's no reason why we can't have an amino acid as we have here, and this is 3-aminopropanoic acid. We'll look at these in more detail when we look at the amino acid groups and in proteins in a following lecture, but we can make a polymerization reaction occur between the amino group and a carboxylic group within the same monomer. So here we would lose the OH and one of our hydrogens here on the nitrogen group. We would form water as a byproduct, and this time we would have a smaller chain repeat unit which only consists of 1 amide group, and therefore we only have 1 water molecule per polymer repeat unit. As I say, we'll look at more of these polymers when we go and look at the amino acids and protein section in the future video. In our earlier work then on esters, we saw that ester bonds and amide links can be hydrolyzed, which means that the breaking of bonds by water or using water, assuming that you've got a molecule which has got a polar bond. So the polyamides and the polyesters can be broken down by hydrolysis because the C double bond O is polar, and therefore, as a result, it is susceptible to nucleophilic attack. And this is particularly advantageous because the addition polymers have got strong carbon-carbon bonds and therefore can't be broken down by nucleophilic attack. And what this means is our polyamides, because of this hydrolysis, are biodegradable. And we're going to go and have a look now in the final section at the different ways of removing, recycling, reusing plastics. So disposing of plastics, we've got a variety of different options available to us. The first thing to note though is unfortunately addition polymers, because of the strong carbon-carbon covalent bond that exists between them, these are non-biodegradable. So we can't simply put those into ground and they won't disappear. However, our condensation polymers, as we've just seen, are biodegradable, which gives them an advantage because they can be broken down by bacteria, and we can also break them down with things like sodium hydroxide. So after the idea of possible biodegrading, if we're not going to use that, that basically leaves us with a few different possibilities. We can bury in landfill, we can burn our plastic as fuel, or we can sort and either recycle or reuse. So issues with burying in landfill, well, in green here we'll have the plus side, it's relatively cheap, and it's also pretty easy to do. On the downside though, it produces things like methane gas, which is a greenhouse gas, and leaks can cause contamination of water supply. The other issue, of course, is that the landfill is continually growing. It's not reducing the problem, and it's just getting larger and larger. Burning as a fuel, well, this is obviously got the bonuses of the fact that it could be used to make electricity, and it's actually a fuel. But at the end of the day, we're still using a fossil fuel, and we can form toxic gases here because if we're burning things like PVC, we might form hydrochloric gas, hydrogen chloride gas, which is obviously acidic. We can pass that through scrubbers, and that would then be to neutralize it, which would be okay. But then at the end of the day, we're also adding to the greenhouse effect because we're going to be forming CO2 in this process. So the final option then is to do some sorting, and we can do recycling. And we can do this in two ways depending on the sorts of plastics we've got. We can either remold the plastic and just make new objects, or we can crack the plastic down, go back through a processing plant, and then remake the new plastics. Obviously, if our plastic is biodegradable, then that makes the whole process much easier. This whole idea of recycling and reusing obviously has its advantages and disadvantages. And we've listed most of them here. The recycling or reusing of plastics. It reduces the amount of waste going into landfill, which is good and saves on raw materials. The cost of recycling is usually lower and it produces overall less CO2 emissions. However, the disadvantages here is it's technically difficult to recycle plastics. Collecting and sorting them is a rather tedious process and is often more expensive than burning or landfill. You can often remake the plastic you started with. You have to make something else instead, and the plastic can be easily contaminated during the recycling process, so you may not end up with such a pure product. What you need to be able to do is make sure you can come up with advantages and disadvantages and compare and contrast and give arguments for recycling plastics in all of these different possible scenarios. So you should now be able to make polyesters and polyamides, or know how we make them, identify monomer units in polymers, recall specific examples of Terylene, Nylon and Kevlar, discuss the disposing of polymers, and identify polymerization in amino acids. That's all for now. Please do subscribe and check out some of the other videos in this YouTube channel. I look forward to seeing you soon. Bye.